Hello and welcome to the final module in TechMar's Advanced Heat Pump Control Training for Radiant Heating and Cooling series. This module is going to introduce the question of the backup heat source. In particular, we'll look at why we consider adding a backup heat source, how do we design for it, and how do we properly control the operation of a backup heat source in conjunction with our heat pump. The outline for the presentation is to discuss the why of a backup heat source, and then how do we pipe it into our design, what are some typical applications, and what are control features that are necessary to consider when adding a backup heat source. Then we'll look at some high temperature applications, and we'll go over how we can pipe those into our system, some applications, and what additional controls we may want to consider for high temperature applications. So what are the reasons a backup heat source should be included in a geothermal system? The three reasons we would consider adding a backup heat source include to provide emergency heat, to provide supplemental heat, and to achieve thermal balancing. The consideration of providing emergency heat would be to address times when our heat pump could be offline. So we don't have the use of our heat pump. Well, what if it is a cold winter's day? What are we going to do to get some heat into our building? So that's a common reason why people consider adding a backup heat source. Now, the question of supplemental heat comes down to if we knowingly undersize our ground heat exchanger and our heat pump because of concerns of capital cost. And that is also a very common consideration because the earth loop is such an expensive part of the system. So we mentioned in earlier modules that it accounts for 30 to 50% of the total cost. So if we can choose a heat pump with a lower capacity and subsequently undersize our ground heat exchanger to provide maybe 70% of the peak load, then we need to consider having a backup heat source in our system to provide heat on those coldest of days. Now there aren't many of those days, so our heat pump is still going to be used for most of the time, almost all of the time, and we can reserve the operation of our backup heat source for those very cold days when our heat pump and earth loop just can't keep up to demand. The other time when we're considering supplemental heat is if we have distribution loads that require high temperature water. So perhaps we have some loads that exceed the capacity of our heat pump. They require water that is at a higher temperature than our heat pump can provide due to its operational limits. So that's another time when we would consider supplemental heat. The question of thermal balancing relates to our earth loop. So we want to make sure that the amount of heat that we are drawing from the earth is equal to the amount that it can also recover. So it recovers heat from the cooling process when the system is rejecting heat back into the earth, and it can also recover from the sun. So what we want to make sure is that it is balanced year round. We don't want to take more heat away from the system, from the earth, than can be recovered. If we do that, if we have a system that is not balanced, then we run the risk of having an unsustainable cycle. And in worst case scenario, it can be a ground loop that is unable to recover. So then we have to scrap the entire geosystem. And ends up being a huge waste of money. So to avoid any type of scenario like that, we want to make sure that our system is thermally balanced, that we are not extracting more heat than can be recovered. And so we could maybe downsize the amount of heating that our heat pump will provide and make up the rest from a backup heat source. So those are the reasons we'd consider adding a backup heat source. We're going to start by looking at emergency heat. So if the geosystem is designed appropriately, we may not need a backup. However, you still may want to include a backup heat source in your design for emergency situations. So you can see in the image here we have a girl who looks very cold. So imagine that this house is being heated from a geo system and our heat pump for some reason goes offline. And so we're cowering in front of a panel radiator that's actually unable to provide any heat. So having a backup heat source for emergency purposes only allows us to avoid this situation so that if our heat pump is offline, we can still provide heat and avoid having a freeze up. Now, if the reason the heat pump is offline is because there's a power outage, then we're probably not going to be able to address that with a backup heat source either. There is a setting in the House Control 406 for the backup delay, and we can set that backup delay to a setting called override. And in that override setting, the backup only comes on if the heat pump is locked out or offline. So we can certainly program the House Control 406 to respect the emergency heat situation and not to operate that backup heat source unless we truly are not getting any heat from our heat pump. This slide contains an image of what I mean when I say we want a thermally balanced ground load. In the winter time, we're going to experience localized ground cooling. So we are extracting heat from the earth for an overall cooling effect in our earth loop. In the summer, we're going to have localized ground heating. In this case, we are rejecting heat from the building into the earth. So our ground loop will experience some heating during the summer. Now, we want the localized ground heating to be as close as possible to the localized ground cooling. In other words, we want thermally balanced ground loads. If we have load imbalances, it can result in ground temperature increases or decreases over time, causing system performance deterioration. To avoid thermal imbalance, we can do one of two things. We can either increase the size of the ground heat exchanger, which as we know would be very expensive, or we can downsize the amount of heating or cooling loads that we will try to obtain from the Earth system. Now, for those of us living in Canada or those of you living in the northern United States, you would experience a heating dominated area where a backup heat source would be recommended. So this makes sense because the geothermal heat pump can take advantage of part load operation. So we don't have to worry about sizing our heat pump and geosystem for 100% of the load. We rarely see outdoor temperatures where that is required. So instead of upsizing our ground heat exchanger and the capacity of our heat pump, what we can do is take some of the pressure off our heating load with the backup heat source and maintain the thermally balanced ground loads. When we're considering adding a backup heat source, what we're really doing most of the time is trying to find the economic balance between full sizing of the earth loop and equipment and the use of a backup heat source. The backup heat source allows us to downsize the earth loop and downsize our equipment, which will lead to significant cost savings. But then we have to account for the fuel costs of operating our backup heat source. Typically, what you find for maximum cost effectiveness is for the heat pump to be sized and for the earth loop to be sized to account for 60 to 70% of the total load. And actually, when we size our earth loop and our heat pump to provide about 70% of the load, they are typically supplying 95% of the total energy used. So normally the amount of time that we have to operate the backup heat source for the reason that the earth loop and the heat pump can't meet demand is actually quite low. It's typically only 5% of the time. Now, we also need that backup heat source if the supply temperatures that our loads need exceed the capacity of our heat pump operating limits. And that's what we're going to look at in this presentation is what kind of design loads may mean that we actually need to have a supplemental heat source because otherwise we're going to see our heat pump trip out on high pressure limits. Once we've decided to add a backup heat source, in this case a backup boiler, into our system, then we have to ask ourselves how do we properly pipe it into the mechanical layout. It actually varies depending on what type of boiler we're using. So if we have a condensing boiler, the best way to include it into the system is on the heat pump side of the tank. And the reason we do that is because condensing boilers will give us the highest efficiencies when the return water temperatures are lowest. So that's what's going to allow the condensing action to take place. So on the heat pump side of the tank, this is where we're going to see our lowest return water temperature. So we can have those lowest temperatures come up to our boiler. We can have the condensing operation to get those higher efficiencies. And then that higher temperature water will come back onto the supply side of the heat pump over to our tank. So we pipe it in this way because we want to ensure that we are operating our condensing boiler so that we take advantage of those higher efficiencies. Now what if we have a non-condensing boiler? Well, here's an example of a cast iron boiler. In this case, we have no added efficiency with cool return water. In fact, we typically have to respect boiler minimum temperatures. So a boiler minimum temperature is usually around 140 degrees Fahrenheit. So I want to make sure that the water coming back to the boiler is 140 degrees Fahrenheit. Now that doesn't mean that that's the temperature of water I want on my distribution side. So having this variable speed injection pump inject water at a certain rate depending on what my target temperature is allows me to have boiler protection and to control the temperature that my distribution system will be receiving. Now here is if we have an electric boiler or an electric element in the tank. Both would be considered electric backup. So our electric boiler in this case is piped off the supply from the tank. Electric boilers do not have requirements for minimum return temperatures. They are able to withstand virtually any return water temperature. So with combustion byproducts and high temperature differentials eliminated, condensation and thermal shock are not concerns for electric boilers. So because of that, we can pipe them directly off the tank supply to boost the supply temperature as needed. And if we are controlling an electric element in the tank, then this would just be turned on and off to boost those tank target temperatures whenever the heat pump was unable to. Once we add the backup boiler to our system, we want to make sure that we are not using the backup more than absolutely necessary. Obviously, our backup heat source is not going to operate nearly as efficiently as our heat pump. So we want to make sure that we're operating our heat pump most of the time, and we're only operating the boiler when needed. So the 406 has some control features that make sure that we are striving for maximum efficiency by minimizing the use of the backup heat source. And the way it does that is by only operating the backup boiler under the following circumstances. The first condition is if the heat pump is at maximum capacity, the tank target is still not satisfied, and the backup delay time has expired. So we could run into this situation if there are a lot of zones calling for heat, and the heat pump and or geosystem and or distribution system were not sized to meet the full design at low temperatures. The other thing that could cause this to happen are high temperature loads. So we'll look at some high temperature loads on the upcoming slides and see how they can boost up that tank target temperature to the point where perhaps our heat pump cannot keep up. If this happens, if the heat pump's at maximum capacity and the tank target is still not satisfied, then we have to wait for the backup delay time to expire. So backup delay is a setting in the House Control 406 that is programmed by the user or installer, and it will hold off the operation of the backup heat source for a certain period of time. Now we can program that up to 180 minutes. So if you set a high backup delay time, you're allowing that heat pump extra time to try to meet the demand before allowing the backup heat source to come into play. The second condition that can cause the backup heat source to come on would be if the heat pump return temperatures are too high. So if this sensor measurement is higher than our heat pump return maximum temperature, we're going to turn off the heat pump and allow the backup heat source to satisfy the demand instead. So those are two scenarios where we would be using the backup heat source. The first scenario is using the backup heat source in combination with the heat pump, whereas the second scenario involves the backup heat source operating without the heat pump. Now we mentioned that high temperature loads can cause that tank target to increase beyond the abilities of the heat pump. So what are some high temperature loads? So here we have an image where we have illustrated a couple of high temperature loads. We have domestic hot water. We have a snow melt system. So here we have our supply water going to a heat exchanger. And the other side of that heat exchanger is our snow melt slab. A pool or spa will also increase the tank target. So here we have, again, we're coming off the supply to a heat exchanger, and the other side of the heat exchanger is our pool. And high temperature terminal units can also boost up those tank target temperatures. If we have some, for example, traditional baseboard as we've shown here in play, then we're going to need higher supply water temperatures, and that's going to increase our tank target. All of these loads have the potential to increase the tank target beyond the operating limits of the heat pump. So we have to be extremely careful when we are adding these type of loads into our system. We have to consider where we should pipe them, if we should size our ground heat exchanger accordingly, or how we can use the backup heat source instead. The first high temperature load we're going to look at is domestic hot water, and we'll consider how we can add domestic hot water operation into our system so that we take advantage of our heat pump when we can. The House Control 406 can control a domestic hot water preheat operation. So here we have a domestic hot water preheat tank that is piped off the heat pump supply to the storage tank. So we have our hot supply water coming up and going into this preheat tank. Now you can see we have cold city water that's going to be circulating through these heat exchangers, and it will collect all the heat it can in this preheat tank before moving over to a second domestic hot water tank. And in this tank we have an electric element that can boost that temperature to the level it needs to be at, and then we're going to pull that hot water out for domestic hot water to our system. Now the downside of the domestic hot water preheat operation is that obviously we can only take advantage of it when our system is in heating mode. So if we have our heat pump switch over into cooling mode, then obviously we no longer will be able to take advantage of this preheat operation. Now, since that is the case, is there an option available that can preheat domestic hot water year-round? Yes, we can take advantage of year-round domestic hot water operation with a desuperheater. And a desuperheater is a small auxiliary heat exchanger that uses superheated gases from the heat pump's compressor for domestic hot water operation. And you can see we have an image here. In gray, we have our heat pump cycle. And we can see that coming out of our compressor, that's when our refrigerant vapor is at its hottest. So that's also where we are going to install the desuperheater. And we have this auxiliary heat exchanger that's going to take advantage of those superheated refrigerant gases in order to heat the circulating fluid for the heat exchanger in the domestic hot water tank. The big benefit to the desuperheater is that we can use it in heating and in cooling. Now, if this isn't an option, is there another way to pipe in domestic hot water into a geothermal application so that we have year-round domestic hot water generation? And yes, the other way we can do that is by relying on a backup heat source instead. So instead of having the heat pump provide a preheat for domestic hot water, we're going to pipe our domestic hot water off of the boiler loop. So the boiler alone is providing heat for the domestic hot water. Now this allows us to have domestic hot water year-round as well, because our boiler can operate to satisfy the domestic hot water targets year-round. So those are our three ways that we can include domestic hot water into a system. We can do it with the preheat in heating mode only with the 406. We can install a desuperheater to have year-round domestic hot water. And we can also pipe the domestic hot water off of a backup heat source. Notice that none of the options we provided included having domestic hot water piped off the tank loop. And there are a couple reasons why that is. The first is that it would just boost up those tank temperature targets way too high to the point where our heat pump would probably be locked out. The second reason has to do with our switchover. If we have a heat-cooled geothermal system, it doesn't make sense to have domestic hot water piped off the tank loop because it won't be able to do any domestic hot water when the tank has switched over into cooling mode. So those are two reasons why we avoid piping domestic hot water off the tank loop. Another high temperature application for a geothermal system is snowmelt. So yes, we can use a geothermal system for our snow melting needs, but we have to take care that we size the earth loop and the heat pump accordingly. If they are not sized accordingly, then we have to make sure that there is a backup heat source in play that can answer those needs. The key control issues when we're including snowmelt operation in a geothermal system are to reduce water temperatures whenever possible and to minimize runtime. So we want to make sure that we are using the lowest possible water temperatures that we can to still meet the demands of the snowmelt system. And that's because, as we all know by now, those water temperatures are so much linked to the efficiency of the heat pump. The other thing we want to do is to make sure we are minimizing the runtime of the snowmelt operation. Snowmelt is a big load on the system. So we want to make sure that if we are extracting heat, we're doing so responsibly because there is a present need for that heat to melt snow or ice. We don't want to run the system needlessly. So control is very important when we're considering adding snowmelt into a geothermal system. Now you can see on the slide here we have pictured a Tecmar snowmelt control and some Tecmar sensors. This is our Tecmar snowmelt control 654, which is our first and currently our only Tecmar Net compatible snowmelt control. And our two sensors, the Snow Sensor 095, which is an aerial snow sensor, and the famous Snow Ice Sensor 090 or 094 over here. And we're going to look at how these controls and sensors work to do these two control features, to reduce water temperatures whenever possible and to minimize runtime. The Tecmar snowmelt control 654 has slab reset, which is a similar concept to outdoor temperature reset that we're all familiar with now. So with slab reset, supply water temperatures for snowmelt can be controlled to remain as low as possible. So you can see how the slab core temperature is going to vary according to the outdoor temperature. And we do that to maintain a constant surface temperature. So let's say we've set up our snowmelt control to maintain a surface temperature of 35 degrees. As outdoor temperatures rise, so does the required slab core temperature. However, as outdoor temperatures drop, then we're going to need a higher slab core temperature in order to counteract the greater heat loss. So this is a way where we vary the slab core temperature based on the outdoor temperature, always with the goal of reducing the supply water temperature as much as possible, which is particularly important in a geothermal application when supply temperatures are tied to heat pump efficiency. Now I mentioned the snow ice sensor 090 or 094. This is a close-up shot of it. You can see it has been installed in some brickwork. And the installation of an automatic snow ice detector will minimize the runtime, or the operating time, of a snow melt system. When we have this sensor, we are going to trigger our snow melt system to operate whenever the sensor detects moisture and the conditions are cold enough to mean that that moisture is snow or ice. So we'll have an automatic start to our system only when there's a need to run it, only when snow or ice is present. Now once that sensor is dry, then we will have an automatic stop to the system. So we're not wasting any of that heat. We are using it responsibly to melt any snow or ice that has been detected. So the snow ice sensor is critical in minimizing the runtime of our snow melt system, which is an important consideration when we're trying to minimize the heating load for the geothermal system. EconoMelt is a new feature for Tekmar snow melting. It is only available on the SnowMelt Control 654, and it allows you to further customize the operation of your snow melt system if you have a snow ice sensor 090 or 094. So let's just say you have a snow melt system, you have your snow sensor for the automatic operation, but you want to reduce the load on the geothermal system by shoveling your driveway first. So as pictured, we can shovel our driveway, and even when we shovel, there's still that thin layer of snow or ice that is very difficult to remove, and it makes for unsafe conditions. So after we finish shoveling, we can manually start our snow melt system at the SnowMelt Control 654 and still benefit from the automatic stop of the snow ice sensor 090 or 094. So we will have a very short runtime of our snow melt system because we've used mechanical means to remove as much snow as possible. And then we're manually starting our system and only running it until that sensor is dry. We're only running it to melt that base layer of snow or ice that mechanical methods cannot remove. So this is another way to reduce the load on the geothermal system if we want to include snowmelt. This first application is showing how a snowmelt system can be off my tank bus so that I am using the geothermal to provide the necessary heat for the snowmelt operation. So here I have my water-to-water heat pump that's being operated to maintain my buffer tank at a certain target temperature. I also have a backup heat source that's being operated for domestic hot water. It can also operate to boost my buffer tank temperatures if the heat pump for some reason can't keep up. Now off the tank loop, I have my one snow melt zone and I have 3 radiant zones. So I'm pulling off the tank loop to a heat exchanger. The other side of my heat exchanger is going to my snow melt zone. And further on down the loop, I have each of my 3 radiant zones. Now, in this scenario, I can also do radiant cooling with these zones because whenever we're operating radiant cooling, it means we're in warm weather shutdown. And of course, when we're in warm weather shutdown, we're not doing any snow melt operation. So just because I have snow melt on my tank loop, it doesn't mean that I'm limited in any way from providing heat and cool for my radiant zones. I can do both. Now we'll look at a wiring diagram for this application so we can see how the controls will be connected together. So here's my electrical diagram to show you the wiring of the 406 with the other controls, the thermostats and the 654 for the application we just saw. So I have my 3 radiant zones, and we will control those zones by connecting heat-cool thermostats to each of the 3 zone inputs on the 406. Now here I don't have a 557. If I'm just doing radiant heating and cooling, I'm going to use a TechMarnet thermostat 553. Now I don't need a heat-cool thermostat in order to do radiant heating and cooling. A heat-only thermostat is able to send a floor cooling call to the 406. But I'm choosing to use a heat-cool thermostat for this application because it is those thermostats that have a built-in humidity sensor. So if I use the TechMarnet thermostat 553 for this radiant heat cool application, then I have a built-in humidity sensor that I need to make sure I'm doing dew point reset. And again, if you have questions about which thermostat to use, a great place to start is this zoning comparison chart on our website. So I have my 3 heat-cool thermostats connected to the onboard zones. Now because that's for radiant, and I only have 1 water temperature, I'm going to configure those zones to be tank zones. Now also on my tank bus, I have my snow melt. So I can connect my snow melt control 654 to the tank expansion terminals. Now I haven't shown you any of the outputs from this control, the pump outputs or the sensor inputs, and that was just to prevent this from looking too cluttered. If you want to see more about the inputs and the outputs from the 654, then I encourage you again to go to our website, and under products you can go to snow melting, and you can see the snow melt control 654, and here you can choose our brochures. So we have a data brochure, and in the data brochure you can find a lot of information about the settings that you would need for the 654. And we also have our application brochure, which will take you through the wiring of the 654. So again, our website's a great place to start when you're looking for more information on how to wire these controls. Now back to our presentation. Now the other control points are what we've talked about before. I have my heat pump and I have connections to R, Y, and the OB directly to the same terminals on my heat pump. For my sensors, I have a domestic hot water sensor, a tank sensor, a boiler sensor, a heat pump return sensor, and an outdoor sensor. So here I'm able to use the domestic hot water sensor because I don't have a mix bus, so I don't need a mix sensor, so I can use the shared terminal input for a domestic hot water sensor. If I didn't want to connect my snow melt to the tank bus and I wanted to instead downsize the earth loop so that I didn't have to provide additional heat for the snow melt operation, I can pipe it off my boiler loop. So here I have shown an application where my snow melt zone is off my boiler loop. So the boiler alone will be operating to provide heat not only for domestic hot water but also for the snow melt zone. And I still have my 3 radiant zones on my tank bus. So we'll take a look at the electrical diagram coming up to see how my control connections have changed. So this looks much the same as the last electrical diagram. The only thing I've changed is that now that my snow melt control is on the boiler bus, I simply moved the connection points from the tank expansion to the boil/mix expansion. So I'm just moving that snow melt control 654 from my tank bus to my boiler bus, and that's it. The rest of the electrical will remain the same. Another high temperature load that we need to design for is a pool or spa application. And just like snow melt, we can pipe these off the tank bus or the boiler bus. Now pictured here is a set point control. We have 2 models of TechMarnet set point controls. We have the 161 and the 162. Now either of these can be used to add a set point operation to our house control 406. Here's an application where I have a pool or spa and I'm piping it off my boiler bus. So I don't want to try to increase the size of my geofield to make up for the additional load of my pool or spa. Instead, I'm just going to use my boiler to provide the necessary heat to keep that pool or spa warm year round. So in this application, I have water-to-water heat pump that is maintaining my buffer tank at a target temperature strictly for my radiant zones. And my boiler is going to be providing the heat for domestic hot water and for the pool or spa. Now this boiler can also boost my buffer tank temperature if for some reason the heat pump can't keep up. Now let's look at the electrical diagram on the following slide. So here's my electrical diagram. It looks similar to the ones we went through for snowmelt, except this time instead of a snowmelt control 654, you'll see I have a set point control 161 or 162. And because in this case my pool or spa has been piped off the boiler loop, I'm going to connect to the boil expansion terminals. I still have heat-cool thermostats in case I wanted to do radiant heating and radiant cooling. Now I don't need a heat-cool thermostat in order to do radiant heating and cooling. A heat-only thermostat is able to send a floor cooling call to the 406. But I'm choosing to use a heat-cool thermostat for this application because it is those thermostats that have a built-in humidity sensor. So if I use the TechMarnet thermostat 553 for this radiant heat cool application, then I have a built-in humidity sensor that I need to make sure I'm doing dew point reset. If I only wanted to do radiant heating and I wasn't concerned about radiant cooling, I could do so. I would just choose a heat-only thermostat. Now, if I did want to take advantage of geothermal heat and include the pool or spa in my tank bus, I can do that as well. Here's an application showing that very principle. So here off my tank loop, I'm going to have my heat exchanger for the pool or spa and my 3 radiant zones. Now, one thing you have to be mindful of in this case is that these zones could not be heat-cool zones if you wanted to have year-round pool or spa heating. So we are limited in that regard. We could not do radiant floor cooling if we wanted to have year-round heating of a pool or spa. So in this case, there would be no switchover of my tank. My tank would be for heat only year-round. From a control perspective, again, since I have at this point 4 zones off my tank bus, I could just use those 4 onboard zones on the 406, and I could connect 3 heat-only thermostats this time, so I wouldn't use the thermostat 557. I would use instead a heat-only thermostat like the 552, and I could use one of those onboard zones for my set point control 161 or 162. Now again, just like snowmelt, you have to be mindful of the sizing of the earth loop because a pool or spa could potentially be a large load. I guess it depends on if your pool is indoors or outdoors. If it was an indoor pool, then it would be definitely a lot more manageable from a load perspective. But just make sure that you have sized that earth loop accordingly if you want to pipe it this way. So this is very similar to the previous example, except I have moved my set point control from the boiler expansion terminals to the tank expansion terminals because it's now on the tank bus. I've also made a note here that these thermostats will be heat-only thermostats. So I would choose a 552 because I'd only be doing radiant heating. I would not be doing radiant cooling. Otherwise, I would be sacrificing heating my pool for the summer months. So pretty straightforward how to connect the 406 to a set point control in order to have heating for a pool or spa application. High temperature heat emitters are also another example of a high temperature load. So here I have some images of traditional radiators and baseboard. And you can see this in a geothermal system if it has been a retrofit. So if you are adding geothermal to an existing layout, then you might have some high temperature heat emitters that are retained from the original system. Now the question is, how do we account for those? Well, in this case, we want to make sure they're piped off the boiler loop. And the reason we want to do that is because we don't want to drive our buffer tank target temperature too high. Otherwise, we're going to see that heat pump get locked out. And we want to avoid that. So make sure if you do have high temperature terminal units that they are piped off the boiler loop. We want to keep them off the tank loop. So here's an example in this system. I have just about everything on my boiler loop. I have domestic hot water, I have a snowmelt zone, I have a pool, and I have a couple of high temperature terminal units. So it is possible to include all these things into a system design. You can take advantage of those terminal units that are in existence, as long as you make sure that you have a backup heat source that can provide all the necessary heat for these high temperature loads. It's hard to believe, but we've come to the summary of this last module already. In this presentation, we covered why we would want to consider incorporating a backup boiler into our design. So we looked at the why. We looked at how we could pipe a backup boiler in to protect the boiler and to try to run our heat pump as much as possible. We looked at some example applications, and we looked at some control point considerations that we need to take into account when we're designing a system with a backup heat source. We also looked at some high temperature applications that might require us to use a backup heat source, and those included snowmelt, domestic hot water, pool or spa, and high temperature terminal units. So for each of those examples, we looked at different piping arrangements, we looked at different applications, and how we can incorporate control into those applications. With the completion of this module, we've also come to the completion of our course for Advanced Heat Pump Control Training for Radiant Heating and Cooling Applications. Thank you very much for signing up and taking this course and for giving me the feedback that you have along the way. It is very much appreciated, and it will be taken into account for future presentations as well. If you do have any questions, like always, send me a message. I'll also give you an email address for questions going forward. So you can feel free to email Techmar at any time with any questions you may have on our controls or our operations. The email address is techmar.customerservice@wattswater.com. So techmar.customerservice@wattswater.com. And feel free to send an email at any time with any additional questions, and one of our customer service representatives will be happy to get back to you as soon as possible with an answer. So thanks again. I really appreciate your attention and your participation, and I wish you all the best going forward. Bye-bye.